Hey guys, we're the Irrational Duo. I'm Kim.
I'm Katie. This is our Team Teach 4, and today we're going to be going over transformation, symmetries, and tilings. So jumping right in, Kim, what are the different types of rigid motion?
So we have a couple of different types. Our first type is going to be translation. And a good way to think about that, and if you just give me a second, I'm getting my annotation tool. And a good way to think about that is we see that this triangle is the same shape and the same size, right? We
Yes.
don't see that it's been rotated, reflected, or anything. So simply translation is just, you just think about a slide.
Mm-hmm.
So it's a slide to a different set of points, but nothing changes about it. The shape, size, all stays the same.
Mm-hmm.
The next one we have is rotation. And this is a little different. We see that we have no slide. And rotation is kind of, so we're going to put no slide. Sorry if you can't read that.
No, it's fine.
um, we're just going to say that rotation is where it's flipped. So we see that this angle right here, this 90-degree angle, is now up here at the top.
I
So
see.
there's also no reflection here. This is no slide. This is simply just rotation. It's just the shape is just
It's just
rotated.
turned.
Yeah,
It's
exactly.
rotated. Okay. Yeah.
So our next one is reflection. And we see that we have this line right here. And this line, if we were to think about like an X and Y graph, this line would be our vertical line.
Okay.
So we see that this is our vertical line. So we see reflection, which we know would still be the same size, same shape, same degree, same angle. It's just simply reflected over the vertical line, almost like a mirror.
Okay.
Um, so it's pretty simple. Also, no slide there.
Okay.
But the next one we have is glide reflection, and it's a mixture between translation and reflection. So if we look here, we see that this glide reflection, this triangle right here, is simply just sliding across. So we see where the slide comes from.
Mm-hmm.
And then we see that we have a horizontal line. I guess I don't have to write that. I could just write x-axis. We see that the reflection would reflect over the x-axis. And again, it's still the same shape, same size. Nothing changes. It's just a kind of like a slide and flip.
Yeah, well, that's great. I like that it's kind of like a building block. And if you know, of course, like the translation, rotation, and reflection, then you kind of can advance into that upper level of then combining the two, and you can really see how the shape moves.
Mm-hmm.
Well, thanks for explaining rigid motion, Kim.
Awesome. So, Katie, what is reflection symmetry now that we're talking a little bit more about it?
So the reflection of symmetry, you touched on it a little bit, and I don't even know that you realized, but reflection symmetry is going to be thinking about, when I hear the word reflection, I think of a mirror. So looking at a mirror, if I have this shape and I was to draw a line, and let me get my pen tool out as well. And I was to draw a line right here, that vertical, or as you were calling it, the y-axis line. And if I was to draw a line there and I was to completely just show the reflection, we would see that this would be the shape that we get. So the reflection of symmetry, and as you also put, whenever you showed us the slide and then flip, it can also be over a horizontal line. It's just whenever that shape is the complete opposite, it just flips over whatever axis is shown. And that's going to be what reflection of symmetry is.
So it's kind of just like a mirror. It mirrors each other. So all the shapes, and so we
Yeah.
see that square, the trapezoid, triangles are all the same shapes in the same
Yes.
place. It's just mirrored over. And I
Yeah.
love that little image you used at the bottom.
Well,
Where
thanks.
he's looking in the mirror.
Yeah, it's really cute. So, on the note of symmetry, Kim, can you help explain what is a line of symmetry?
Of course. So a line of symmetry is a two-dimensional shape, which is a line such that when a mirror is placed on it, one half of the shape reflects over the other half. So we've been doing a lot of the reflection, so line of symmetry plays a role in that. So
Okay.
if we look at our equilateral triangle, we see that if we were to like mirror reflect this image, we see that we would have three lines of symmetry because those
Okay.
3 lines of symmetry, if we were to mirror it, they would all be the same. Looking at our square has 4 lines of symmetry. Our regular pentagon has symmetry. And then our regular hexagon would have 6 lines of symmetry. And I say regular because that means it's original, because we have, other pentagons of different shapes and
Of
hexagons.
course. Yeah, shapes can be kind of tricky.
Of course. So it kind of just plays a role into reflection, like what we talked about before. So if it can be reflected, it has a line of symmetry, like cut in half, or diagonal, whatever. It's all kind of the same.
Yeah. Well, thanks for sharing.
Of course. So now that we were talking a little bit more about reflection and symmetry, could you explain what rotational symmetry is?
Absolutely. So this one I'm actually going to need your help on. So let's first start off by kind of giving you a resource.
Okay.
So this is what's called a protractor. And some of the main points that we talk about on a protractor are common degrees. So a protractor is used to find the degree of a shape or an angle. And some of them that you've already even talked about is going to be that 90-degree angle. So right here.
Sure.
So that was that, perfect, and I can't draw a perfect triangle, but I'm sure going to try. That perfect triangle, whenever you see that little box right there, that is understood that it's a 90-degree angle. So that's what it means. You could take this protractor and place it on maybe not this angle, but a perfectly drawn angle, and you would see that it's a 90-degree angle. So, this isn't, of course, all of the degrees. You could take another protractor and we see right here that it's 180 degrees. So you could actually take another protractor and put them together and you'd form a whole circle. And if you put those measurements together, then we would know, of course, that a circle equals 360 degrees. So let's take a look at some of my smiley faces here and see if you can help me guess what the degree change of each, or degree rotation is of each shape. So keeping in mind that this smiley face here is going to be our original, okay? So let's take a look at the middle one and we see that it turns. So noting that the smiley face started here and he went all the way around to here and he stopped. So using our protractor, if we were able to move it, how many degrees would you guess that our smiley face turned?
I would honestly guess it's 180, because looking at the protractor, we could see, like, if our 90-degree angle was, just in fact, if it was the original, if it's only turning upside down and not fully, then it would be 180 degrees. So that's my guess.
Yes, and that is correct. It just turns halfway, which is half of a circle is 180 degrees. Now this next one, I'm going to warn you, it's a little tricky, so watch it, okay? You ready? All right. So we see that it looks exactly the same as the original, but it did turn. So do you want me to draw again how it turned?
Sure.
Okay, so we started, of course, here, and he kept turning. He went all the way around until he reached that point again. So how many degrees would you say we turned?
I would say it's 360 degrees, because looking at our 180 degrees, we see that that is half of 360. So if we think of a full circle, we see that 180 is half of it. So the full circle would be 180 times 2, which is 360.
Absolutely, Kim. That's great. That's a great way to think about it. Even putting that math into it, you could absolutely say, I did turn half and I did turn half. Add those together, and I know that's 360. If you didn't know, that a circle is 360 degrees. Well, thanks, Kim, for helping me out with that.
Oh, yeah. No, that was awesome.
Yeah, well, so looking at our next question, could you help me find the exterior angles of this equation?
Of course, of course. So I kind of just did an image because I love this visual and representation of it. But I'm going to write on it as well, just so I can point out a couple things. So how I think about this, I'm going to label this A, B, and C. and then
Okay.
we're looking for x over here.
Okay.
So we know, and this is the way I learned it, but I'm actually going to show you this way first
Okay.
because we were talking about 180 degrees and everything. So we know that a full, so a line like this would be 360 degree. Well, 180 degrees is half of that.
Okay.
So I know my visual sucks right there. Just drew it.
No, it's great.
So we know that we have 180 degrees, and then we're going to subtract it by angle C here. So this is angle C. And then this will give us angle X. So 180 minus 71 will give us 109 degrees. So that's easy. But the
Okay.
way I like to think about it is that we have A and B here, and we're looking for X, which is the outside. So X is going to equal the sum of A and B added together.
Okay.
So we see that 64 plus 45 equals 109 degrees. And like we said, we could take that and find angle C. If this was missing, let's just mark that out. So this is angle X, right?
Okay.
That goes right here, angle X.
Okay.
But if we were looking for angle C, and I love how this kind of plays a role in together, if we were looking for angle C, this is kind of like, we would take angle X and subtract it by 180. And then that will give us 71 degrees, which is also angle C. So we could, if we have one or the other, we could solve, for either one.
Yeah.
So we could also solve for angle C and for angle X. But we already had angle C. So, it's just kind of a easier way to remember it.
Absolutely.
It's a very easy and great visual. That's why I like to do it.
Yeah.
But
Well, I think that's great. And I wouldn't have thought about sharing with students that if you know how to work it one way and then you know how to work it the other way, you can actually use each way to work it
of
to
course.
kind of check yourself.
Yeah, and it's kind of like the deal with if you have one, you can find the other,
Absolutely. Yeah. Well, that's great. Thank you.
Very welcome. So, talking about that, could you, now that we've found, how to find exterior angles, which are angles on the outside, could
Yes.
you help us find interior angles that are on the
Yes. Yes. So, like you said, interior angles, you kind of already answered it, but a clue, if you get confused, interior has the word inside the shape. The angles inside the shape is what we're looking for. So let's take a look at a hexagon. We have a formula to find the interior angles. So that formula is n minus 2 in parentheses times 180, which we know, of course, is the full degrees of the shape, divided by n equals the sum of the interior angles.
Okay, well, I have a question. What would n equal?
So I'm glad you asked. So n is actually going to equal the number of sides. So the number of sides in any shape that we have. So we're going to use a hexagon for this example. So for that, all we would do is just count the sides. So I have 1, 2, 3, 4, 5, 6 sides. 6 sides is going to be, or 6 sides in my hexagon. So 6 is going to equal n. Okay? So from there, all we're going to do is we're going to plug in the numbers into our formula. So we're going to start, of course, with our first half here. And so we entered in 6. So 6 minus 2 times 180 is going to equal 720. So, but that's only part of the problem. So we have to go ahead and plug in the other part. So 720 divided by n, we know n equals 6, which is the number of sides, equals 120 degrees. So that's safe to say that each of these interior angles is going to equal 120 degrees.
Well, that was easier than what I thought it was going to be.
Yes, absolutely. And it can be a little confusing at first, but just remember to always, even for me, I get so excited. I'm like, oh yeah, I know how to do this. I know how to plug in those numbers. But I think where Some students get a little ahead of themselves and they go ahead and turn in an assignment without completing
Yeah.
the entire equation. You have to go back and look at the formula and almost rework it again to make sure that you answered the entire problem.
Of course. And I also love that you put what n equals, because we could always go back and look at that and make sure we understand what it equals, what we're looking
Absolutely.
for in.
Absolutely. I always like to write down the facts, write down what we know. That way we don't forget anything.
Of course, of course.
All right. Well, jumping on to the next thing, Kim, can you help us explain, or can you explain to us, what is the difference between how do you say it?
Postulates.
Postulates. So what's the difference there?
Okay, so we have 4 different kind of postulates. And they're kind of difficult, but we learned about this in our video notes, and that's why I kind of wanted to point it out, because I didn't know either. I had to actually, not only watch the video, but kind of like Google and refer to make sure I understood what they said doing our homework. So they're also, they're called postulates, but a lot of people refer to them as properties. So,
Mm-hmm.
And they're both the same things. They're all kind of like referring back to congruency. So we have the side by side postulate, which is SSS, and we put these in parentheses so we don't have to say side by side the whole time.
Yes.
Which we see the image there. We have 3 pairs of congruent sides, So we have, we see that we have the line. Let me circle this. We see that we have the lines on here. Sorry. We see that we have the lines right there to show us where our congruent sides are.
I see.
So we also have side angle side, which is also SAS.
Mm-hmm.
We not only have 2 pairs of congruent sides, we also have 1 pair of congruent angles. So not just the sides are the same, the degree of the angles are also the same. So we see here we have a congruent angle, and we have a congruent angle, and then we have to at least have 2 congruent sides.
Okay.
We also have angle side angle, which is ASA. We have 2 pairs of congruent sides and 1 pair of 2 pairs of congruent angles and 1 pair of congruent sides. So we see we have 2 angles here, and then we also have a congruent side.
Okay.
And then our last one is side angle angle, which is SAA. We have 2 pairs of congruent angles and 1 pair of congruent sides, but the sides not between the pairs of angles. So we see down here at angle side angle,
Mm-hmm.
our congruent side was between these 2 angles, correct?
Yes.
So we see that would have been right here, but it's not. It's now up here.
Oh,
So,
I see.
Yeah, so each postulate or property is kind of like has its own set of, I don't want to say formulas, but has its own set of how would I say it? Standards, I guess.
Yes.
For each one to refer,
Yes.
which property we know would apply to that angle. So hopefully that sums it up a little bit. It's a lot to, intake, but also things like this we would not expect our students to know on their own.
Yes.
But like you
I
said,
really like your visuals.
Oh, good. I thought this image was actually pretty unique because it not only explains it, it gives us our, visual, and exactly, it shows us exactly what we need to see and not more or less.
Yes, absolutely. Well, thanks for sharing, Kim.
For sure. So now could you help us find the vertex of shapes and angles?
Yes. And so this one, I'm going to use your help again.
Okay.
So for this, in one of our previous team teaches, you actually helped us figure out what vertexes are. So you said that vertexes are where any of those corners meet. So I put some shapes in here, and some of them are a little tricky.
Okay.
But we're going to look together and we're going to circle each of the vertex or the corners of each shape. So let's start off with this star. So I would say that our first one would be here.
Of course.
And then it meets here.
Mm-hmm.
And it just keeps on going.
Of course. And I feel like students wouldn't necessarily even consider that a point, even though it's like concaving in and not convexing.
Mm-hmm.
I believe, and one's concave and one's convexing.
Yes.
I think they would skip over those ones that are coming inwards instead of outwards because
Yes.
they're not pointy, but they are. They're,
Yes.
where any two angles meet together.
So did I get them all?
Oh, yeah, I think so.
Let's see, I missed one up here. So
At the
I would
top.
say that this star has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This star has 10 vertex or vertices.
Vertices, yeah.
Yes. Oh, I missed my R. That's okay.
It's all right.
Good
We
thing
know.
this is math, not spelling, huh? Okay, so let's take a look at another shape, and we're just going to do the same thing. So this is a cube. So
Mhm.
obviously we can't see all of the sides of our cube. So we're only going to do what we can see.
Okay.
So let's just start, and I see one here,
Of
and
course.
here, one here, and one here.
Mhm.
So I see that I have 4 there, and we
Mhm.
know that, is it 6 or 8 sides of a cube? Let's
I'm
see.
pretty sure it's 6.
I think it's 6. So instead of circling each of these, we can't
Mhm.
even see the back of them. But if
Yeah.
we know that we have 6 sides,
Mhm.
or 6 squares to make up a cube, so we could say 6 times 4, and then we would know how many vertices we have. So 6 times 4 would be 12, 24.
Let me double check you. Yep, for sure.
24 vertices or vertex.
Mhm.
Sorry, I have everyone driving down my road. They're being so loud. Okay, so let's take a look at another one, and this one might be a little tricky. Kim,
Ooh.
do you see, first of all, this is a cylinder.
Mhm.
So with the cylinder, a cylinder is another 3D shape, of course. So we have another circle on the bottom, just as well as there is on the top, and it goes all the
Yeah.
way around. So kind of something that we could, give the students if we didn't have access to those 3D shapes is like a can of soup.
Yeah.
So Kim, are there any vertex on a can of soup or this cylinder?
Looking at the image, you could be pretty deceived to say, like, you could be deceitful because you can't see the full image or realize if it's a 3D shape. I think the students would guess that's a vertice,
Mm-hmm.
or as if like down here that would be a vertice, but it's not because like even this cup, it's not necessarily a cylinder, but I have no points or edges on this cup.
No
It's
corners.
yeah, no corners, exactly. Thank you for the
Mhm.
better word. But we could see there's no corners on this cup. It's full on 360 here. So
Absolutely.
I would say no, it has no vertices, but like you said, an image could be very deceitful without holding those shapes in the
Yes.
classroom for the students to
So
see.
you are correct that there are no vertex or vertices
Mhm.
here in this shape.
Of course.
But it's something that even I was like, wait, are there? But there are not. So it's a tricky one, but I put it on there for good reason because it would trip up me and it would trip up our students. So that's why I went ahead and put it on there for our review
No,
today.
I'm glad you put it on it. I'm glad that's something that, is very useful to review about because, images and not being able to see things, you know,
Hmm.
shapes, especially when it comes to shapes and cubes and
Of
cylinders and
course.
stuff like that. You have to see that in person.
Of course. All
Um,
right. So jump into our next question. What does it mean to be congruent, Kim?
well, we've talked a lot about congruency earlier when we were talking about our properties and postulates. So this is kind of just to go more into depth about that.
Okay.
Um, so congruency would mean that two angles are congruent. The degrees of each angle are identical. So the
Okay.
degrees of every shape and angle are the same. Though the size and the shape of two congruents are equal, the orientations may be different. So orientation is kind of like the layout of it. So
Okay.
when we were talking about our rotation and our glide and reflections earlier, that's kind of where it plays a role in it because our images may look the same,
Hmm.
may have the same shapes and angles, but they may not look the same, is what I
Hmm.
meant to say.
Okay.
So looking at our first image, we see that these angles and shapes they all look the same. There's no rotation, there's no reflection here. we could see that A, B, and C is congruent to D, E, and F. And we can
Okay.
also see that the angles are the same, and we can see the shapes are in the same place to each other.
Okay.
So looking here, though, we are looking at this, correct? So when we're talking about congruency, we're not only saying they are equal to each other, we have to put this little squiggly line to understand congruency. That's
Okay.
just, a visual representation to say, hey, these angles are congruent to each other.
Okay.
Or our next image, the shapes could look like this. So we see that our purple triangle here has A, B, and C as well.
Mm-hmm.
And our green triangle also has D, E, and F.
Mm-hmm.
And they're still equal to each other because we could see this angle here is corresponding and congruent to this angle here. And
Mm-hmm.
that goes for the other two as well. And
Yes.
we could even say that for our exterior angles. So we know that we see that 7 centimeters here, like we learned before, we know that this would be our base.
Mm-hmm.
So our base is now up here at the top. So that does have rotation. And it could also be a reflection as well. We could also have a horizontal line and that be reflecting, underneath it.
Yeah.
So it's kind of just, to be congruent, you have to have the same angle, size, and shape, no matter if the orientation is different. So that's why I chose these two images, because you could see when one looks exactly the same,
Mm-hmm.
or when the orientation is, completely different, but we could see that all of our angles and measures here are equal. So
Yes.
this would still be A, B, and C are congruent to D, E, and F. It's just in a different orientation.
Absolutely. Well, thank
So
you for sharing.
yeah, for sure. So now that we talked a little bit like that, we can move on to um, talking about our pentagon. Let me clear my,
Absolutely.
sorry, or penta, I mean.
Yes. So PENTA is an acronym for the word, which you already kind of gave it away, but that's okay,
Yeah.
for the word Pentagon. So PENTA is an acronym or is short for Pentagon. So a penta or a pentagon has 5 sides. So when we're constructing a pentagon, we know that it should equal 5 sides. So we have a little trick for that. Obviously, this to us is a pentagon or a penta,
Yeah.
but a trick that we can teach our students is to spell out the word penta. So what we're going to do is we're going to label. So our top will be P,
Yeah.
our next side will be E, the next side will be N, then T, then A. So if you can spell penta, you can tell if it's a pentagon or not. So
That would have been so useful when I was in school, because I would have not realized, if we're using the acronym for pentagon and just saying penta, I could count the sides and be like 5 letters, 5 sides. It's a pentagon.
yes,
Oh, I did
absolutely.
not even realize that.
Yeah, well, that's I love, using for students little weird ways. We talk about that all the time in our team teaches that,
Every team
you
teach,
know,
we have to bring that up.
that, the silly little things are what students remember. So I think that's a great silly little one. We could probably even come up with a rhyme or something for it too.
Mhm. Yeah.
All right. So moving on to our last, part of our last question. So Kim, how would we determine the height of a cliff?
Okay, so doing this homework question was a little confusing because you had to convert a couple of things before you could solve anything in this problem.
Mm-hmm.
So, but we would do cross multiplication here, and what we would multiply is, we see that she has 2 feet of roller,
Mm-hmm.
and that would be over 1.5 inches apart marks. So each inch, all the apart marks were 1.5 inches away. And then
Yes.
we have she's a quarter of a mile away from the cliff. And then we're looking for the height of the cliff. So let's just go ahead and convert, like I said, what we need to do first. So if we're trying to put everything into feet, so we can find the height of the cliff in feet and not in inches.
Okay.
Because we're talking about distance. So,
Mm-hmm.
we're usually talking about feet or miles,
Yes.
not inches.
Mm-hmm.
So we know 1.5 inches, converting it to feet, would be 1.5 inches over 12 inches would equal 0.125 feet, and then a quarter of a mile would equal 1,320 feet.
Yes.
So doing cross multiplication, I'm going to point this out here. This will cross multiply with that. and this will cross multiply with that. And I think that's a little confusing for our students because they might think this is what we're multiplying or this is what we're multiplying, but cross multiplication means,
Makes an X.
or they might think that this is supposed to multiply with that, and it's not. So cross multiplication.
Yes.
So we see that we have 0.125 multiplied by 1,320, and that was in feet, would equal 2, which is the 2 feet of roller, multiplied by the height. So we would get 165 equals 2 times h. Well, we want to get height by itself, so we would divide everything by 2. So dividing height by 2, that will mark that out, and 165 divided by 2 would leave us with just h, and h would equal 82.5 feet.
Okay.
So we know the height of this cliff total is 82.5 feet.
Wow.
So, yeah, it's a lot to take in, but, it's kind of just like a, step-by-step process,
Yes. Well, I think that's a great way, to explain it to students, though, and we're being exposed to a lot of different concepts of math. So I think that's great. That's great. And that was a really great explanation.
Thank you. So now that we were talking about how to find the height of the cliff, we had to talk a little bit about converting.
Yes.
Well, can you go into more depth about how we would convert inches into feet?
Yes. So whenever we think about converting inches into feet, there's kind of one main thing that you need to remember, and that is we're going to look at a ruler here, and we know that in between each of these here, in between these spaces equals 1 inch. So right here we have 1 all the way to 12, and these aren't actually inches, obviously, for this, but that's okay. We have a snip of this ruler, so we know that there are 12 inches in 1 foot. So to convert that, we would just divide however many inches you have by 12, and that would be, our how many feet we're going to have. So if you want, Kim, we can work one together. Why don't you give me a number?
So let's just say I have 4 inches.
4 inches?
Yeah.
Okay. So we're going to do 4 inches. Oh, that is supposed to be an S. That's okay. So we're going to divide however many inches you have by 12. So divide by 12. So we're going to do 4 inches divided by 12 inches, and I'm going to use my calculator because we're going to get a fraction.
So, and we're dividing by 12 inches because there's 12 inches in 1 foot, correct?
Yes.
And so,
yeah, so if we type that into our calculator, we actually get this answer here, and the 3's go on and on and on and on forever. So what we can do is we can convert this decimal, the decimal. I was like, wait, is it called something else? We're going to convert the decimal into a fraction. And so to do that, if we were to do that, then we would have 1/3. So 4 inches equals 1/3 of a foot.
Awesome.
Yeah.
So, I mean, that was more simpler than what I thought it was.
Yes. Yeah. It's a little confusing at first, but, if you can get started, then you can do it. And bigger numbers are a little bit easier to do because you wouldn't get like a small fraction. But, yeah, that's all I have on converting.
Okay. All right. I think that's all we have.
All right. Well, thanks, Kim.
Thank you.